Alrighty, in this lesson we are going to be talking about power series, and they are going to be series where we have a variable x and then we have a sub n being constants. So in this case we have the summation from n is equal to 0 to infinity of this lovely thing right here, and if we expand it out it's going to look like this, and then we could also say the same thing whenever it's centered at 0. The sum of the series is going to be a function f of x is equal to this lovely thing right here, which we saw right here. And that's going to be important because the domain of f of x is going to be the set of x values where the series converges. So essentially for today's lesson, our main goal is to find out when x converges so that the power series converges. Now, your c value, whatever that is, will always be in the domain. Now, the domain, like I said, we kind of have a special word for it, and it's called the interval of convergence. The interval of convergence is the set of all x values to which the power series converges, aka my domain. So, there you go, new vocab. All right, so we kind of have some possibilities for convergence for our power series right here. So it can converge when x is equal to c. This basically happens whenever our test diverges, and if our test diverges, then the only x value that will converge will obviously be whatever your c value is. Now, if your series converges absolutely for all x values, then that's going to be us having a domain of all real numbers. Great. And then part 3, there's going to be a positive number r such that the series converges absolutely. When we have the absolute value of x minus c is less than r, and it will diverge in the opposite direction. So if we have the absolute value of x minus c is greater than r is going to be called the radius of convergence, and that's going to be the distance from the midpoint of the interval of convergence the distance from the midpoint. This is the distance from the midpoint to, I don't know why I said to the interval of convergence. There you go, that makes more sense. And for the most part, whenever we are trying to find r, we're going to be using the ratio test. So thinking back about Unit 2 and how we found the ratio test there. All right, so let's go ahead and look at the power series for number 1, and we are going to find the radius of convergence, and we're also going to find the interval of convergence. The first thing that I'm going to do is go ahead and do my ratio test. Remember, for the ratio test, we are going to have let me actually write it. We're going to have a n plus 1, and then we have over a sub n. And for convergence, remember that our limit has to be less than 1. So that's our goal for convergence. All right, gonna clean this up. X to the n plus 1 over x to the n is just gonna be x. And then I have n over n plus 1. Since I'm taking the limit as n approaches infinity here, and both of them have same degrees and the same coefficient, this tells me that this right here will converge to 1. So now I have the absolute value of x. Now, remember back in Unit 2, right here, if we want to find convergence for the ratio test, my limit has to be less than 1. In this case, I have a little restriction telling me that we have the absolute value, and that has to be less than 1. In this case, hopefully you guys remember your Math 3 skills. So that's going to give us negative 1 is less than 1. Negative 1 is less than x, which is less than 1. Notice, so here, this is going to be your radius of convergence, aka 1. So r is equal to 1 because it's in this format. And then to find my interval of convergence, that's just me solving the absolute value inequality. So negative 1 is less than x, which is less than 1. Now, as a disclaimer, this is not my final answer, because what I forgot to mention at the beginning was that we will need to test endpoints for the interval of convergence to see if -1 converges or diverges, and to see if 1 converges or diverges. Because I already know between -1 and 1 that any number between -1 and 1 will already converge. All right, so what we're going to do now is go ahead and test our endpoints at -1. If x is -1, I'm going to have the series -1 to the n over n. Now, because I have a -1 to the n, this is an alternating series test. Remember that I have two conditions for that. Is my series, or is my sum, not my sum, my sequence, my terms, are they decreasing? So are my terms decreasing? Yes. Because if I have 1 over n, that's going to be 1 over 1, 1 over 2, 1 over 3, 1 over 4. That's going to be decreasing, so that's good. And then is my limit, if I take the absolute value of it, 0. Well, we know that -1 to the n is just 1, so 1 over n is going to approach 0. So we know that by the alternating series test, when x is equal to -1, this tells us that the series converges. Since my series converges, I'm going to go ahead and have a little less than or equal to symbol there. And then I'm going to test +1. 1 to the n is just going to be 1, so that's why I have it like this. Now this right here is a harmonic series, and we know that if I have a harmonic series, automatically I know that the series is going to diverge. So when x is equal to 1, this tells me that my series diverges, so I'm just going to keep it as less than 1. All right, so this tells me two things. This tells me that my radius of convergence is r is equal to 1, and my interval of convergence is between -1 and 1, where we are including -1 right here. All right, that's number 1. Let's go ahead and do number 2. Number 2, we have 2n factorial, and then we have x over 2 to the nth power. We are going to go ahead and do my little ratio test. All right, so I have this right here. I'm going to try to simplify this to be 2n plus 2, just so that it makes my life easier. Now I have the limit as n approaches infinity, and then I have this right here. I'm going to do this first because this is easier. This is just x over 2. Now I'm going to look at this right here and figure out if my limit diverges or converges based off of this. Now, through common sense, because I have 2n plus 2 factorial and I have 2n factorial right here, this is going to tell me that my numerator is going to grow faster, which tells me that this limit is going to be divergent. Now, I'm going to prove that by doing it by using the algebra way. We know that 2n factorial is the same thing as 2n plus 2, 2n plus 1, 2n, 2n minus 1, 2n minus 2, and so forth. We know that 2n factorial is 2n, 2n minus 1, 2n minus 2, and essentially all of this right here will cancel out. Which means I'm only left with 2n plus 2 and 2n plus 1. And like I said, this right here is going to diverge. Now, because my ratio test diverges, remember that my series will converge when x is equal to c no matter what, because it's always in my domain. So in this case, my c value is going to be 0. Since my c value is 0, this tells me that my radius of convergence is x is equal to 0, no, r is equal to 0, and then my interval of convergence, aka my domain, well, in this case, the only one is going to be my c value. In this case, it's 0. So my interval of convergence is x is equal to 0. All right. Number 3. We have this lovely thing, so I'm going to go ahead and use the ratio test. -1 to the n plus 1, x to the 2n plus 2, 2n plus 3. I'm going to go ahead and make it pretty just so that I don't have to do it later. And then same thing here, 2n plus 3 factorial. Going to multiply that by the reciprocal. And now I'm going to make things pretty. If I have 2n plus 1 factorial here and 2n plus 3 factorial here, remember that 2n plus 1 factorial is this. And then 2n plus 3 factorial, the only thing that doesn't get canceled is the 2n plus 3 and the 2n plus 2, because everything else will come up here, and that's going to cancel out. So at the bottom, I have 2n plus 3 and 2n plus 2. On top, let's see, I have -1 to the n plus 1 and -1 to the n. So that's just -1. And then if I have x to the 2n plus 3 and x to the 2n plus 1, I'm just left with x squared. All right, so as I take the limit as n approaches infinity of this lovely thing right here, this tells me that I have 0. Oops. 0. So this tells me this is 0. So now I have -1 x squared times 0. Well, in this case, because this limit is 0 right here, let me just do this, 0. And since 0 is always less than 1 in terms of my ratio test, this tells me that any x I plug in, I substitute n, this right here is going to be convergent, no matter what. Always convergent. All right, so this tells me that my interval of convergence is going to be all real numbers, and then my radius of convergence is just going to be infinity. Great. All right, I'm going to do one more, and then we're going to do one more. That's an application. All right, number 5. We have n, and then we have x plus 2 to the n over 3 to the n plus 1. I'm going to go ahead and use my ratio test. Oops. And then I'm going to make everything nicer. So in this case, I have n plus 1 over n. So that's good. This is good. My x plus 2 to the n plus 1 and my x plus 2 to the n is going to be x plus 2. That's good. My 3 to the n plus 1 and my 3 to the n plus 2, I'm going to have 3 to the first power in the bottom, right here. And of course, this has to be less than 1. All right, now my limit right here, this right here, n plus 1 over n is just going to be 1 since we're looking at coefficients. So technically now I have x plus 2 over 3, which is less than 1. Now to find my radius of convergence, remember that the radius of convergence is in the form of x minus c is less than r. Now I have this 3 right here that's kind of a menace. So I'm going to multiply by 3 to get this lovely thing right here. So we have the absolute value of x plus 2 is less than 3, which tells me that my radius of convergence is going to be r is equal to 3. Now I'm going to solve this inequality to find my interval of convergence, aka my domain. I'm going to subtract 2 from both sides. And that's going to give me -5 and +1, or so I think. Remember now, once we get to this part, we are going to be plugging in -5 and +1 into my series to figure out if the series converges or diverges. So I have this lovely thing right here. I'm going to rewrite -3 to the n so that it looks like -1 to the n times n, 3 to the n, and then 3 to the n plus 1. Now 3 to the n and 3 to the n plus 1, this is going to be 3 at the bottom. So I have this lovely thing right here. And now I could use the alternating series test, because this is alternating. Now, based off of the alternating series test, my limit right here, though, it's not going to be pretty because this is going to diverge. So this means that I can't use the alternating series test. Okay. Since I can't use the alternating series test because that fails, then maybe we'll have to use the nth term test, because that's going to be essentially the same thing except without the absolute value bars. In this case, this right here diverges. Since this diverges, this tells me that my series right here diverges. So my series diverges by the nth term test. Boo. We're also going to plug in 1. So now I have n, 3 to the n, 3 to the n plus 1. So this right here is going to be n, 3 to the n over 3 to the n plus 1 is 3, so n over 3. Well, this right here grows without bounds, so by the nth term test again, this is going to diverge. Since both series diverges whenever we have x is equal to -5 and x is equal to 1, this tells me that my interval of convergence will not be including them. So we'll just only include the intervals between -5 and 1, but not -5 and not 1.